In 1998, researchers looking at the Honolulu Heart Program found a striking statistic. When they studied a group of retired men, the death rate over a 12-year period was twice as high for those who walked less than a mile a day compared to those who walked more than 2 miles a day. Looking at a simple graph of those numbers, it is tempting to draw a straight line from X to Y. You walk more, and therefore you live longer. But the researchers didn't assign who walked and who sat. The men chose their own routines, and that leaves an open question. Did the intense walking actually extend their lives, or were the men who walked 2 miles a day simply younger and more physically capable to begin with? This problem is known as confounding bias. It happens when a lurking third variable influences both who gets a treatment and the outcome of the experiment itself, mixing true causes with pure coincidence. This diagram shows the actual relationships in the Honolulu study. Notice the variable for age at the top. It creates a fork, pointing downward to both walking and mortality. Because of these diverging arrows, math cannot distinguish the benefits of walking from simply being young. Whenever variables fork like this, raw observational data becomes ambiguous. You cannot determine a clear cause and effect just by looking at the final numbers. The traditional statistical fix for a known variable like age is straightforward. You compare the intense and casual walkers within specific age brackets, essentially leveling the playing field. But researchers know that other, unmeasured variables might still be lurking. To protect against this, the default practice for decades has been to measure every possible data point and mathematically adjust for all of them. Political analyst Ezra Klein pointed out just how absurd this can get. Studies will proudly list off everything they controlled for: income, religion, hair color, whether someone drinks Coke or Pepsi. The longer the list, the more rigorous the study appears to be. But throwing every variable into the math is wasteful and dangerous. By blindly adjusting for anything that can be measured, researchers often end up controlling for the exact mechanism they are trying to study, muddying the data even further. Filtering data without a clear structural map of how causes relate to each other is entirely guesswork. To truly isolate a cause, scientists needed a physical mechanism to force nature's hand. In the 1920s, statistician R.A. Fisher faced this exact problem at an agricultural research station. He wanted to know if a specific fertilizer actually caused higher crop yields. Out in the fields, nature is chaotic. The yield of any given plot of land is influenced by a massive web of variables: unpredictable weather, soil composition, drainage, and existing microflora. Looking at this diagram, you can see how those environmental factors create a tangled web. They influence not only how well the plants grow, but also which fertilizer a farmer might choose for a specific patch of soil. Fisher realized he could bypass the farmer's bias entirely. He proposed using a randomized deck of cards to dictate exactly which plots received which fertilizer. Because the plants cannot read the cards, and the cards don't care about the soil quality, this random assignment completely detaches the fertilizer from the surrounding environment. Notice the change in this diagram. The incoming connections to the fertilizer are deleted. The random draw is the sole decider. By erasing those arrows, Fisher created a mathematically pure environment. Now seeing an outcome and applying an intervention are identical. This technique became known as the randomized controlled trial. It remains the standard for clinical science today because it acts as a physical tool to sever confounding variables in the real world. But we cannot randomly assign everything. We cannot force a group of people to smoke to measure the health effects, or rewrite history to test a different economic policy. The insight of modern causal inference is that physical randomization is no longer the only way to sever the arrows of a complex system. In this simulated model, researchers can construct an accurate causal diagram and mathematically pinpoint the exact variables, the deconfounders, needed to clear the data. This allows scientists to look at messy observational data and isolate the true effect of an intervention without performing a physical experiment. By shifting our focus from fearing hidden variables to mapping how they actually interact, we finally have the architecture required to interrogate nature and answer the question of why.